Chapter 3: Internal Energy and Enthalpy. Section 3.9: Bomb Calorimetry. Chemicals combust in a bomb calorimeter under the isochoric condition, and therefore the reaction heat is equal to the internal energy change of the chemicals in the system. Let's look at the diagram of a bomb calorimeter. So we have a temperature reader. This is to monitor the temperature change of the system. And we have a bomb right here with a constant volume condition. We have sample inside. The sample may combust in pure high pressure oxygen. And over here we have fuse wires connected to the ignition box. We usually just push a ignition button to send the electric current through the wire, and the wire will be ignited first, which will in turn ignite the sample. And over here we have a stirring motor and a stirrer. This is to ensure the temperature is even inside this calorimeter. Now, how can we actually compute the enthalpy of reaction given the internal energy of the reaction? We have to do some theoretical derivations. H is defined to be U plus PV, and therefore delta H is delta U plus delta PV separately. And now if we can somehow measure the reaction heat, we will get this internal energy of reaction. But how can we get this delta PV, the PV change of the chemical system? Again, in this bomb, chemicals combust in high pressure pure oxygen, and then from the reactants to the products, the PV actually changes. But how can we account for the PV change? So first, we will neglect the PV change of liquids or solids, only because the PV change of a liquid or solid is much smaller than the PV change of a gas. So over here, this delta PV is approximately the delta PV of gases only. And for gases, we will use the ideal gas law to estimate PV, and PV is approximately nRT. And then we will estimate this delta nRT, the change of nRT. If we use a large water bath, the temperature change of the reaction will be very small. It's just because although the combustion heat can be significant, if we use enough water, the temperature change of everything inside the calorimeter may undergo a very small temperature change, for example 2 degrees Celsius. And then if the temperature goes from 298 K to 300 K, then this nRT changes just very small. So really this R and this T are treated as constant. Okay, R is indeed a constant. It's just we treat the temperature of the reaction also as a constant, even if the temperature increases during the combustion. However, this N is not a constant because we have a chemical reaction. This N is the number of moles of gases, and in chemical reactions we may have the number of moles of gases change. For example, if you combust benzene in oxygen, we will produce water and CO2. The number of moles of CO2 is very likely different from the number of moles of oxygen as a reactant. So delta U and delta H of the combustion reactions differ. They differ by approximately RT times the change of moles of gases. And because delta U and delta H of a combustion reaction is in the order of 10 to the power 3 kilojoule per mole, and this term is in the order of only 10 to the power 0 kilojoule per mole, that's why it's okay to make so many approximations, because if we have a for example 5% error for this delta PV term, it's not going to affect the delta U or delta H of this reaction significantly. And note that this delta N gases is unitless, because the physical meaning of this is the change of the number of moles of gases per mole reaction. We need to divide a mole in the end. So again, by looking at this diagram, we notice this water bath. We use a large water bath to absorb most of the heat released from the combustion. And again, this ensures the accurate measurement of the initial and final temperature because we're trying to make sure the temperature is even inside the calorimeter. And also, the water bath prevents the bomb from being overheated. One more reason is this: we ensure the temperature of change is really small. Again, from 298 K to 300 K, the change is even less than 1%. Therefore, from here to here, well, even though we introduced some error, the error is actually less than 1%. Alright, we made 3 approximations in this theoretical derivation. First, H is U plus PV, that's exact. From here to here, it's also exact mathematical derivation. But from here to here, we're assuming the product of PV of a liquid and from a solid is much smaller than those from gases. Again, it's just because the volume of gases are much larger than the volumes of liquids or solids. And now from PV to nRT, we assume it's an ideal gas. And from delta nRT to RT delta N gases, we assume T is a constant and R is a constant. We can take R and T out of this delta. However, this N actually changes because N sub gases is the number of moles of gases, and delta N gases is the change of the number of moles of gases per mole reaction. And very often we have different coefficients in front of the gaseous chemicals in a chemical reaction. So again, we're going to talk about the 3 approximations one by one. Over here, from here to here, we assume the change of PV of liquids and solids are negligible compared with that of gases. This approximation introduces about only 0.1% error in the calculation of this. 0.1% error is because the volume of a liquid or solid is usually only 0.1% of those of a gas. And then this is ideal gas law, PV equals nRT. This will introduce roughly 1% error in the calculation of this. And now here we assume the temperature is constant. That's why we can take the temperature out. What if the temperature actually changes by 1% from 298 Kelvin to roughly 301 Kelvin? Well, it does introduce roughly 1% error to this calculation. But overall, if we make the approximations for delta PV to be RT delta N gases, we introduce up to around 2% error to this. And this is, by itself is small enough. This is about 10 to the power of 0 kilojoule per mole, and then multiply by 2%. So the error is pretty small. Making this 3 approximations is reasonable. In this bomb calorimetry experiment, the combustion heat is absorbed not only by this large water bath, but also by anything else inside this calorimeter, which includes the bomb, the stirrer, the water bucket. Actually, there's a water bucket that holds the water, and also there's air on top of water, and there's inside surface of this calorimeter. All of these items absorb heat. Therefore, the heat capacity of everything inside the calorimeter is called the calorimeter constant. It's denoted by C sub calorimeter. Now let's look at one example problem, 3.9.1. The combustion of 0.01 mole standard chemical X raises the temperature of the water bath by 2 Kelvin. The internal energy of combustion is negative 2000 kilojoule per mole. The amount of water is 2 kilograms. Now let's calculate this calorimeter. Okay, this heat capacity of calorimeter is the total heat capacity minus the heat capacity of water. So first, let's compute C total. That's the heat capacity of everything inside, including water. How do we compute this? We have the amount of the substance, 0.01 mole. We have the internal energy change of the combustion, 2000 kilojoule per mole, by multiplying the number of moles and this internal energy change of combustion, we get 20 kilojoule. That's the amount of heat released from the combustion. And now this amount of heat divided by the temperature change, which is 2 Kelvin, we get 10 kilojoule per Kelvin. This is the heat capacity of everything inside the calorimeter, including the water. Now we need to subtract the water. So it's 10 kilojoule per Kelvin. Subtract the heat capacity of water. We have 2 kilograms of water, and its specific heat capacity is 4.184 kilojoule per kilogram Kelvin. And we do this calculation, in the end we get 1.632 kilojoule per Kelvin. So the calorimeter constant is 1.632 kilojoule per Kelvin, and this calorimeter constant is the heat capacity of everything inside the calorimeter, excluding the water.